Welcome back to Aldehyde and Ketone Land. So remember the way this chapter is organized. We are looking at the aldehyde and ketone as kind of the star. It's the functional group that is getting attacked at its carbon because that is electrophilic thanks to that dipole. And so a nucleophile is therefore attracted to it and will attack and open up that pi bond. The fate from there on out depends on the mechanism, but they do have some similarities. So studying the mechanisms will help you feel like there's more patterns to be seen here than a long list. And so what we've covered so far are how oxygen nucleophiles, which ones are relevant and that you need to know, and nitrogen nucleophiles. And what we're going to cover today, we will completely finish hydrogen nucleophiles. We'll start carbon nucleophiles. So let's get started with hydrogen nucleophiles. Now, hydrogen nucleophiles might be surprising because we have been thinking about, like, what do you think of hydrogen's role usually? Usually we think of hydrogen back in even just general chemistry. We're always thinking about it as a proton, right? We're thinking about acting as a proton. So in the sense we would think of it as maybe even on water. We draw the dipole, corresponding dipole, where we see, okay, well, there's a delta plus here because oxygen's more electronegative. Therefore, hydrogen gets picked up by something that has more negative character, that's attracted to it, right? So a base would come and grab it, for example. That is not what's going to happen here because hydrogen is going to be a nucleophile. It's going to be the exact opposite. In order for that to happen, we have to essentially reverse this polarity in that bond to hydrogen. So the only way to really have that happen is to have hydrogen bonded to something that is less electronegative than it. And that's where these transition metals come in. So it could be aluminum or boron. So the electronegativity of aluminum is less than hydrogen, which flips that dipole so that we have a delta plus and a delta minus. Likewise with boron, we've seen that before, by the way, with hydroboration. That effectively allows it to act as a hydride instead of a proton. So there are two reagents that we're going to know, and one should be very familiar, NaBH4. Like I said, we've used this before, sodium borohydride, and lithium aluminum hydride, abbreviated LAH. So that's lithium aluminum. Notice the name hydride. They both act as delivery agents for a hydride ion. You can almost kind of think of the easier, simple mechanism as it's almost like it's giving you an H-. It doesn't truly dissociate from the metal and act as a lone H-, but that's essentially what you can kind of simplify it to. So let's do the mechanism. I won't do it really long. I'll write it in a way that's acceptable for simplifying it. So we're going to take LAH, first step, and it's always worked up with water because this is a nucleophile, basic conditions, and so that's going to need to be quenched later. In other words, we're going to have anions that are hanging around and we're going to just have water there to quench it. By the way, it's not always shown, it's sometimes implied that you're going to have a workup. However, the complete route would have those two steps. So look at our product for just a second. We have our our aldehyde and or ketone, and we converted it to an alcohol. So what's the new bond? The O has a bond to H, and that carbon, which used to be sp2, is now sp3 and tetrahedral. So what is that fourth bond to it? It's the H from the hydride, right? So furthermore, notice that because it's sp2 and now it's sp3 tetrahedral, and especially if this is an R prime where those two groups aren't equal, we are going to go from something that's not chiral to chiral. So you got to watch out for that. So what we call the reagent beforehand is prochiral. It means it's not chiral at the moment, but it's going to undergo a reaction where it becomes chiral. So watch out for prochiral things because they can make you overlook enantiomers when they're formed at the end. So this would be a racemic mixture. because remember the sp2 is planar. Okay, so what's that look like? So the important pieces of LAH to draw out: the lithium is basically a spectator ion. It's the aluminum, it's Li plus, AlH4 minus. And so you can draw that lithium if you want over here, or leave it off. And as a simplified mechanism, I'm going to draw the bond, so the electrons, with the hydrogen. So I don't just, the hydrogen can't attack. You need electrons that always need arrow from electrons. So the bond is going to attack and open. So essentially, everything from here on is going with it. So the hydrogen's going with it, right? So that's that new H that we see later underlined in red. So that's our nucleophile. Okay, so then if we keep tracking that H, so I'm going to circle it in green this time, since it was circled green there. If we keep tracking that H, our intermediate part of the mechanism, we'll have attack open, so we have the O minus like we typically do, and we have our new H. I'll circle that in green. Okay, so that's what we're left with, is an alkoxide ion. So that's why we need to do step 2, which is the water step: simple acid base, clean it up, work it up, quench the anion. And when you're asked to show mechanisms, that's not always necessarily part of it, but it's good to keep those simple things in mind so we don't lose sight of it. Okay, so that's workup. Okay, so in other words, aldehyde or ketone in the presence of LAH or NABH4, we can get alcohols with our new H attached to the carbon. But beware of the chiral centers, right? And we're going to do some, this was a template to get you started, but we're going to do some very specific examples so that we can get an idea of where we might have some possible pitfalls. Okay, so I've got 4 kind of representative examples, but of course when you're doing homework, you're going to want to do way more than that. I might even modify these to add a few more. Predict the product of each of these reactions. Okay, here we go. You might even want to stop and do this ahead of me. LAH, workup, aldehyde. We expect an alcohol with the H from here. Okay, so I'm going to circle that H. That's going to be our new H in green from that mechanism. I'm not drawing the mechanism this time unless you have to. I'm just using my understanding of the mechanism to say, okay, I know I attack open protonate. I got an OH there for that reason. I have an original H to begin with, and I have a new H, which was the one in green. Now, tracking the H's is important. I'm doing that in green here. There's another way we do that, which is with deuterium. So I'm going to actually modify this to see if we can predict that. How about we do deuterated LAH? In other words, LiAlD4, which is the same as writing LAD, right? So this is also the same as LAH, just another way of writing it. Followed by a water workup. Can we predict, in other words, remember that deuterium is just heavy hydrogen, has the same reactivity, same mechanism, so where do we put the deuterium? So, you need to know the mechanism, right? How did the mechanism work? The hydride attacked the carbon of the carbonyl. So the deuterium, the D minus, is going to attack the carbon of the carbonyl. So instead of having that green circled H, we're going to have a D now. The original H stays there. The O used to be an O minus. It was attack open. Step 2, protonate. Notice the water was not deuterated. The water was the same old H2O, so that means this is H. So to track that part, I'm going to do that in red here. This H is responsible for that one. And now notice a difference. Here, I have something achiral because I had an aldehyde, and when I added an H, and I already had an H there, I didn't get a stereocenter. But because I added a D, that's still different than an H, so I have a stereocenter now. So watch out for those things. Deuterium is really popular question on some of the exams. the harder homework problems. So once you work through the ones without deuterium, that's your next level. Okay, that's a way to kind of work your way up. Okay, let's start. Let's do a sodium borohydride example. Now notice it's not always shown as separate steps. It's much milder, and it can even be mixed with a protic solvent like methanol or an alcohol and still work. And so that's usually how you'll see it written instead of having separate steps. And so we'll just have OH there. So the new H, you can draw the H if you want. I didn't draw it. That new H came from here, right? But if you look at your answer key, it's going to look like this because we don't need to draw it. And notice because of that plane of symmetry, this is not chiral. So there's no new stereocenter to point out. Now LAH is has a nucleophilic hydrogen, hydride, right? So it's a little bit reactive, in other words. It's pretty strong. It will react with more than one electrophile. So look at this molecule. We have two functional groups present, an alkyl halide and a ketone. Both of them have a dipole. Let's just draw the positive parts because that's where the hydride will be attracted to. I mean, of course, if you want, we could draw the whole thing. But the nucleophile is going to want to attack either one of these two. Now, LAH is so reactive, it doesn't really take its time to discriminate, and it will attack either one. So I will draw the LAH here, and I will show that whole H, and we'll have a problem if our goal was to make the alcohol. Well, we might not have done that first. We might have actually made the alkane right there first. So notice the leaving group's gone, and now it's a CH3 instead of a CH2Cl. We would need another equivalent available of LAH to reduce the ketone. So, moral of the story here is that LAH is strong enough. It's a strong reducing agent. Okay, what does that mean? It attacks other electrophiles too. So watch out for LAH. Sodium borohydride. Can we say the same? Let's suppose we look at sodium borohydride and react it with the exact same starting material. Well, you're learning two for a reason. That's so you can have this power to discriminate. If you wanted all electrophiles wiped out, LAH is your go-to. If you don't, if you only want to attack your carbonyl, then sodium borohydride is what you want. So it's going to ignore, so even though we have a delta plus here and a delta plus there, it's going to preferentially attack the carbonyl delta plus because it's a weaker, slower reducing agent. It only reduces the carbonyl. So our final product will keep the chlorine. You'll see my little pictures I'm trying to show in a minute. And don't forget there is a stereocenter now. So I'll write this out in words. Sodium borohydride only reduces the carbonyl. It's a weaker reducing agent. So it reminds me of, just to kind of keep them straight, I'll pause for a minute to tell you a little bit of a story about my garden and an analogy I saw there. Spending a lot of time in my garden these days, and if you do any gardening, you might get frustrated if you see, this picture was taken in my garden, this kind of critter. And my son likes these. He'll keep them as a pet so that I don't have to have them. You can see all the leaves he's eating. Grasshoppers, they eat basically any plant. They're really not picky. You put any leaves in their terrarium that he has, and they will eat them. They're one of the biggest destroyers of gardens, and just in order to not harm them, my son will feed them in a separate spot so that they're not eating everything that we're growing. So they'll eat anything. They're kind of like the LAH, if you will. And so let's put this guy over here. He's the grasshopper. He eats anything, attacks any electrophile. However, another critter in the garden that's just perfectly welcome on my end, because in fact, I plant plants for it. It's like pet food. It only likes one plant. It will only eat one plant, and that's milkweed. So that's the monarch caterpillar for the beautiful monarch butterfly. And you can see right there, and right there's a couple of them. And that caterpillar won't go and eat any of the other plants. It will only eat the milkweed, which I grow for it to begin with. So I'm quite happy with that. So keeping that in mind, that's kind of like the sodium borohydride. It's much more selective. So sodium borohydride is slower, not as reactive, not as aggressive. It takes its time. It picks its favorite functional group, which is the carbonyl, and it is more attracted to the carbonyl, right? That's the CO bond versus the CCl bond. That's a greater attraction with the dipole difference. So there's a reason for that, but it takes its time to make that wise decision. Whereas lithium aluminum hydrides, like the grasshopper, it's so hungry and voracious, it doesn't care if it's found its favorite plant or not. It eats whatever's there. And so lithium aluminum hydride is like that. It doesn't care that this dipole is less than this one. It will attack either one, the first one it encounters. So you want to attack both. You go with LAH. You want like full-blown reduction. LAH is your go-to, and it's a very popular reagent for that reason. And especially if you have no conflicting functional groups, it's actually a favorite because you get really great yield. It just goes to completion. Sodium borohydride is really nice if you're trying to be very careful about other functional groups present, which is very likely in a research situation with a bigger molecule, like a pharmaceutical drug, which has lots of functional groups that are reactive, and so sodium borohydride will be more targeted, and so it'll be a little more ideal. Okay, so moving on. I've said this word many times, but it helps to kind of categorize this. This was a reduction reaction. So we've done reduction, we've added hydrogens, but just to kind of put it in context, we were usually doing it with an alkene, right? So this is the last time we spent much focus on adding hydrogens, where we added these H's across a pi bond. So we are adding one H on the pi bond. We're getting rid of the pi bond, and we're adding one H instead of two. Now, because it's a reduction, and alkenes can be reduced, and carbonyls can be reduced, let's think about that as an additional confounding possibility. So in other words, just like we had a problem before, we had a problem where we had two possible electrophiles, and we solved the problem by saying, okay, LAH, that's going to be the one that wipes out both of them. NABH4 is the one that will selectively only touch the carbon nucleophile. Electrophile. We could have another problem. We could have another pi bond that could get reduced. So what happens when we have those two functional groups present? A pi bond, an alkene, with another type of pi bond, a carbonyl, both which we know undergo reduction. Well, I will show you the results and why we have to consider other reagents to help us with that. Okay, so notice this little pattern we have going here. 3 starting materials that are the same, 3 different reagents over the arrow. The first arrow is what we've seen before, sodium borohydride with methanol. The next one is H2, which we've used on alkenes before. But this is a special kind of catalyst cocktail. It's more of a slurry, technically speaking, called raining nickel. And so it's a specific way of preparing the catalyst that allows it to undergo the desired result here. And then, so it's this excess of hydrogen versus one equivalent of hydrogen in Raney nickel. So let's just see how the different outcomes are affected, because we know hydrogen will touch that. We know sodium borohydride will touch that. But if we have an excess, we'll both go. In other words, that's kind of the question. All right, so sodium borohydride. We know it's that little caterpillar, and it will not affect our other functional groups. It really likes the carbonyl. It's attracted to that dipole, and there's not a dipole in the alkene. And those hydride nucleophiles, so in other words, NABH4 and LAH for that matter, do not reduce alkenes. So alkenes are safe in the hands of the hydride nucleophiles. Only carbonyl is reduced. Okay. Now, if we have an excess of hydrogen gas in the presence of the Raney nickel slurry, excess meaning more, as many equivalents as you need to react everything there, we will in fact see a full reduction. Probably not a big surprise, right? Because just as it can add across a CC pi bond, it can add across a CO pi bond. So Raney nickel in excess will reduce both. Okay, so there's 3 scenarios you might want. We might want only the alkene touched, not the carbonyl. Luckily, if you control stoichiometry, you can have that. So in other words, we could have only the alkene reduced and keep the carbonyl, because the H2 Raney nickel does preferentially go for the alkene first. So if you only put in one equivalent, you will only reduce the CC bond. So that's pretty handy. That gives us various permutations where we can target different types of reductions. Okay, so that's it for the hydrogen nucleophiles. And next, we are going to go in to carbon nucleophiles. That's a big one. So I suggest getting this done kind of quickly. This one's a little more straightforward. The carbon nucleophiles is a bigger section, a lot more to it. So start practicing this now, take a break, come back fresh for the carbon nucleophiles, and I'll see you soon.